I've come up with it. I'm pleased with myself now. Right, I've seen the light. We are going to use the least upper bound property of the real numbers because look at the set. Look at the set. Let's call it S for set, which we'll define to be all the x's which are an element of CD, such that P is true at x. Okay, by the least upper bound property of the real numbers, this has a supremum, but that's a contradiction in terms. So by the least upper bound property, by the LUB of the real numbers, S has a supremum. I don't know if I've done a video on the least upper bound property. You can prove it really nicely using the Dedekind cut definition of the real numbers. Okay, so S has a supremum. Why is that a contradiction? Okay, so supremum of S, supremum of this set S, is either an element of S or it's not an element of S. Either an element of S, or it's not an element of S. Element of S. If sup of S is an element of S, that implies that that P is true at sup of S. Why? Because sup of S would only be in S if P is true at X. So if sup of S is an element of this set, P must be true there. Okay, so there exists an epsilon greater than 0 such that that little interval such that if x minus sup of S is less than epsilon, it implies that P is true at X. Okay, what next? P is true at X, but that's a contradiction because because X is greater than sup of S, and X is an element of S. So it contradicts sup of S being the supremum of S. So that's a contradiction. If sup of S is not an element of S, then that implies that P is not true at sup of S, which implies there exists an epsilon greater than 0 such that if sup of S minus X is less than epsilon, then P is true at epsilon. P is not true at X. So what I'm basically saying is, okay, if sup of S is not an element of this set on which it's true, then there exists an interval down here, a little epsilon here, such that all the points in here, it's not true either. But that's a contradiction, because these, is that a contradiction? Yes, it is a contradiction. It contradicts sup being the supremum of a set of points which are of this set of points, because these, all of these points in here, X, these must all be greater than or equal to S, where S is an element of S. It must be greater than all the elements in this set that this was greater than. But X is less than sup of S, so X would be a better choice for your supremum, so it contradicts this being the supremum. So basically, this set having a supremum is contradicted unless sup of S is equal to D. That's the only point that you don't get a contradiction, an instant contradiction from. And that's it pretty much. You get... I suppose I should... there wouldn't have been a contradiction either. Okay, sorry, yes, I need to prove one last little bit. Okay, so unless sup of S is D. The other alternative is that sup of S was equal to... So this was the choice of sup of S... so all of this argument here implied that sup of S was some element of CD, the open interval. I need to check that sup of S equaling C is not a contradiction. Well, that's obvious, because if it's true at C, we know it's true at C, then there's this interval in front of it on which it's true. So all of those would be elements of the set, so it would contradict C being the supremum of that set. So C is out the window as your supremum. Any point in between here is out of the window as being your supremum. So the only point that can possibly be your supremum is D. So what we have shown is that the statement P is going to be true on the entire interval CD. So P is true on CD. Okay, so now what you just do, let P equal the statement that f of x is greater than 0. Okay? And then you just apply this induction. So all we need to show is that, so if P is true, we need to show that there exists, this epsilon, such that if you go epsilon in front, if you're within epsilon in front, then it's also greater than 0. Well, you just use continuity now. That's where we're going to finally use continuity. So if f of, let's say, little p, in fact we used little q, didn't we? If f of little q is greater than 0, then by continuity, there exists... Oh, well, okay, let me just draw a picture to show you what I mean. So if we have this function, so we have CD here, we have our function f, we have our little point p here, q rather here, which is slightly above 0, and it's something like that. Well, basically, then by continuity, well, let me just do this. So we have some f of q. We can this has some value, so it's here, and it's greater than 0. So pick an epsilon such that it's less than f of q. So I want you to take an epsilon ball around here such that the epsilon is less than here. I don't want the epsilon to go over the x-axis. I want the epsilon to be ball to all be above the x-axis. So I pick epsilon less than f of q. Then by continuity, there exists a delta greater than 0, such that, this ball of size delta around here, this is the delta ball around f of q, such that if y is an element of this ball around q of size delta, so this ball, if y is within this ball, it implies that, f of y is an element of the ball around f of q of size epsilon. So basically, if I make this delta small enough, I can assure you that it's in this interval, which implies that if y is an element of this ball of size delta around q, then f of y is greater than 0, because I specifically chose the epsilon so that it would be greater than 0. So just let this delta be your epsilon, and I know that's really confusing, that I've used epsilon here to mean something different from the epsilon up here, and I've used delta to mean the epsilon that I meant before. But use this delta as your little sort of interval in front where it's going to be true. So if you use this delta, it's true that on here it's always going to be greater than 0. So use this delta. Use this delta as your epsilon, epsilon in the continuous induction process. Okay, new piece of paper, and we will continue. Where were we? So we now need to prove the other property that we needed, which was this one down here, that if it's not true at a point, then there's an interval backwards where it's still not true. Okay, so it's exactly the same proof. You just use continuity again. So if q bar is an element of CD, such that it should be an element of the open interval. But yeah, we don't want it to be C or D. Well, it could be. No, actually, we do want it to include those. So it's the closed interval. CD. Okay, such that f of q is less than 0. Okay. Then again, we'll pick q. It's q bar, isn't it? So draw another picture, and it's exactly the same argument. D. So we've got q bar here, with q bar here, we've got f of q bar here. Q bar, f of q bar. Okay, so let epsilon be less than, again, less than the modulus of f of q now, because f of q is going to be negative, so take the positive version of it. Because it's negative, the modulus is just equal to negative f of q. But that's the intuition. I want epsilon again such that, you know, it's not going over this x-axis. I want to be assured that when I map it onto the delta ball around here, that it's going into here, and then it's going to be less than 0. So, by continuity, there exists a delta greater than 0 such that the ball around q bar of size delta is all mapped into the ball around f of q bar. Oh, q bar, I did put q bar there, of size epsilon, which implies that this entire ball, the ball of q bar d, that if I take the image of this, all these points are less than 0. These points are less than 0. Okay, so just let that be your delta that you're going to use going backwards, and you've got this little little strip down here that's such that all of these points going backwards is less than 0. Therefore, by continuous induction, since f of c is greater than 0, i.e. the statement is true at c, it implies that f of d is greater than 0, but that contradicts our initial assumption. And that implies that there must have existed a point where f of x was equal to 0. There exists an x which is an element of CD such that f of x is equal to 0. Now, why does it go wrong if that's the statement? Because if there's a point where it's equal to 0, if there was a point where the function was equal to 0, then neither of these statements hold. These two things here, these two go wrong. No, not that. These two things here go wrong. You cannot say that there's an epsilon in front of it such that it's greater than 0, because, for instance, if you have a function that just touches 0 there, like that function there, it just touches it, but all epsilon you take in front of it are going to be less than 0. On the other hand, you could have a function like this, which touches it from this side, so you have a point where it's equal to 0, but in front of here, all of the epsilons are greater than 0, so you cannot say either of these statements are true for a point where it actually is equal to 0, and that's where the argument fails when there is a point where it's equal to 0, because that point is a valid supremum of our set where the statement is true, basically, and that's why the argument fails if there is a point where it's equal to 0. So the fact that if there isn't a point where it's equal to 0 leads to a blatant contradiction. Implies that there must exist a point where it is equal to 0, providing the function is continuous. Of course, if the function isn't continuous, then this doesn't work at all.